Share my screen. We're not doing that yet. All right, let me get the iPad connected and then we'll get started. So we're going to do, I've kind of 3 different questions that are kind of practice questions related to solutions and concentrations. So if you have done your videos from Tuesday and kind of started work on the practice, then hopefully these will make sense to you, or you'll hopefully be able to follow along and kind of answer or chime in as we're going through and I ask you guys stuff. So all right. Okay, so can you guys all see the practice questions on here?
Yes, I can see them.
Okay. Hopefully that means everybody can see them. Okay, so these are practice actual, multiple choice questions like what you would see on an IB exam that have to do with solutions and concentration. And so what we're going to do is we're going to go through them and we're going to see if we can figure out sort of kind of what are they asking us for and how would we answer these questions. So I'm going to bring my highlighter up here. So this says, what is the concentration? So that means that I am solving for C. I'm solving for my concentration. Notice that it specifically says in moles per dm to the -3. Okay, so that means specifically they're asking us to solve for the molar concentration. And I told you guys in kind of the video from last time that molar concentration is like probably like 98, 99% of the time, that's the concentration that we'll be using in questions. The other ones where it was, the mass per volume or it was the part per million, you do need those occasionally, but the vast majority of the time, it's going to be this molar concentration that it's involved with any of our questions for our practice stuff. Okay, so anytime I see those units right here where it says like mole times dm to the -3, so that's moles times decimeters to the -3 power. That's the same thing as me saying moles per decimeters cubed. Okay. And so remember, IB doesn't like these units with the numerator and denominator, so they're always going to flip anything in the denominator and make it look like multiplication. And so that's why the dm is raised to a -3, because really it's a 3, but it's in the denominator. So when we want to make it flip it and make it like the inverse, that exponent becomes negative. Okay, that's just a math thing to remember. Okay, so once again, so these units tell me it's molar concentration. And so what else do they give me? Well, they also tell me that I have 20 grams of my compound, and they tell me the compound is sodium hydroxide. NaOH is sodium hydroxide. They give me a volume. They tell me the volume is 500 cubic centimeters. So this is a volume. This is a mass. Okay. And then this other number that they give me here in the parentheses, if you remember all the way back to kind of the beginning of Unit 1, anytime I see this capital M with kind of the subscript R, that is the relative molecular mass or the relative molar mass. Okay, so the R just means relative, but remember capital M is always molar mass. Okay, and so they've given us the molar mass that we need. They're not going to make us calculate it because they know that we don't have a calculator, because on multiple choice questions, we never have a calculator to use on the test. And so you notice they've already rounded it. It's 40, so it's a whole number. So all the numbers they gave us are whole numbers, 20, 40, and 500. And so the reason they do that is because they know you don't have a calculator, so they're going to give you numbers that are easier to do math with kind of on paper or in your head. Okay. So we're solving for the concentration, and specifically it's the molar concentration. So what that means is I need to do, I know my concentration is the number of moles divided by the volume. That's my equation to solve for molar concentration from the notes. However, the issue here is they did not give us the number of moles, okay? They did give us the volume, but they didn't give us the number of moles. Instead, what they did is they gave us the mass and they gave us the molar mass. And anytime they give you the mass and the molar mass of something, you can use those items to convert the mass into the number of moles. And so what I would do first is I would say, okay, well, I have 20 grams of that NaOH, and they told me right here the relative molar mass is 40. That means that it's 40 grams for every 1 mole. That's what relative molar mass means. It's the number of grams of that substance in 1 mole. So I can do a really quick one-step conversion and just use the molar mass to convert from the mass to moles. And even though I don't have a calculator, you should be able to divide this in my head, right? Because 20 divided by 40, that's just like if I took the zeros off, that's like 2 divided by 4. So what's 2 divided by 4? Or 2 over 4. I think about that. Yeah, so it's a half, right? And so I'll just call it 0.5. And so I get 0.5 moles. And so 0.5, that's the number that's going to go up here for my N in the numerator. Okay, so if I plug that in, so concentration is going to be 0.5 moles, because that's what we just figured out the number of moles were. Now for the volume in the denominator, what number is going to go down there?
500.
Okay, are we sure? So I want you to...
Oh, wait, do you have to convert it something?
Yes, exactly. So I told you guys in the notes that a lot of times the volumes are going to be given to you in cubic centimeters because that's typically what we measure in the lab. All of our lab equipment measures in milliliters, which is equal to cubic centimeters. So a lot of times the volumes you're given in the question or in the problem are cubic centimeters because that's naturally what you measure when you're collecting data. But in our equation, we talked about, look right here, the volume is cubic decimeters. It has to match. So I always have to convert any volume they give me to cubic decimeters before I can put it down here, okay? And we talked in the notes, it's really easy because cubic centimeters, I just divide by 1,000. And so that means that I am just going to move the decimal 3 places to the left. So if it's right here and I move it 3 places, 1, 2, 3, that makes it become 0.5 cubic decimeters. Okay, so that's actually the number that goes in the denominator because I have to convert it from these cubic centimeters before I put it down there. So now I'm dividing, but look, it's the same number divided by itself. So what's the answer going to be?
1.
Yep, 1. So that would mean my answer would be C. So again, is this a little complicated? I mean, yes, there were some more than a couple steps involved, but again, all the numbers that they give you to work with are easy. So if you remember all the different parts, like, you know, make sure you convert the mass to moles so that you can put that in the numerator. Make sure your volume is converted to cubic decimeters before you put it here in the denominator. Then these 2 numbers were so easy that it's just 1 and we didn't really need a calculator. Okay. All right, so let me scroll down. I'm going to erase this area here so I can have some room to rewrite. Okay. All right, so this one, we have an antacid tablet. Do we know what antacids are? What's an example of an antacid tablet? Like from the store?
Suddenly everything left my mind.
So like Tums or like Maalox or like Pepto-Bismol is not a tablet, but that's a liquid antacid. So all of those like stomach medicines, those are all antacids because they all help your upset stomach, because the whole point of them is they all neutralize your stomach acid. Because typically if you have an upset stomach like that, it means that there's too much acid. There's too much hydrochloric acid in your stomach and it's getting out of the stomach lining area where it's supposed to be kept. And so when it gets out of there and it starts getting into your esophagus, that's when you start feeling like that weird heartburn feeling, or you start feeling really nauseous and it hurts. And so you take antacids, and there's several different kinds, but all antacids, they're all different kinds of bases. And so bases always neutralize acids. And so the whole point of taking an antacid, no matter which kind it is that you are reacting the base that's in your antacid tablet with the extra acid that's in your stomach that's getting out in order to neutralize it and get it back to that normal level of acid so that you're not feeling sick anymore. So an antacid tablet, says it contains 0.5 gram or 0.5 grams of sodium bicarbonate. So sodium bicarbonate is the chemical name of baking soda. So baking soda is a base, okay? And then they've given us the molar mass here, okay, of the sodium bicarbonate. So they gave us the molar mass, and then they've given us the mass right here. Okay, so right now that tells me, since they gave me a mass and a molar mass, that tells me most likely I'm going to have to convert that mass to moles. Okay, that's going to be part of the setup probably, because they wouldn't give me both of those if I probably didn't need to do that. But if we keep reading, it says an antacid tablet containing 0.5 gram of sodium bicarbonate that has a molar mass of 84. It's dissolved in water to give a volume of 250 cubic centimeters. Okay, so in my head right now, I'm going to go ahead and I'm going to convert this to 0.250 because I know that it has to be cubic decimeters. I know I have to divide by 1,000. Okay, so that's kind of a good habit to get into, is automatically converting volumes to cubic decimeters in the question, because if it's a calculation like this about concentration, you know you're going to have to convert it anyway. And then it says, what is the concentration? And again, it's the molar concentration in the solution. Okay, so kind of the same question. We're doing the same thing we did on number 1. It's just this question's worded a little bit differently. It's just a little bit wordier because they talked about it being an antacid tablet and all this stuff. So, you know, it's the same concept. It's just worded slightly differently, but they gave us the same information. So I know that I'm still going to be solving for the concentration. So I need the number of moles divided by the volume. Okay. And then the number of moles I'm going to have to solve for, right? I'm going to have to convert it. And so I know that I'm going to have to do 0.5 grams, right? And I'm going to have to divide by this molar mass, this 84 grams. So we don't have a calculator, right? And this one's not as easy as number 1. But if you look at all the answer choices, all the answer choices are equation setups. So they're not expecting us to actually solve for the answer. They just want to know, can we set it up correctly? So with that in mind, I'm just going to kind of simplify this. So remember, 1s don't change our number. So really this setup is 0.5 divided by 84, right? Because 0.5 is on the top and 84 is on the bottom. So essentially here I'm doing 0.5 divided by 84. We agree with that, or we see why that is?
Yes.
How about Abby and Javon? You with me still?
Yes.
Okay. So that's the number of moles, right? Because doing this calculation up here, we're solving for n. So I'm going to plug this division in for n in this equation. Okay. And then I'm going to plug this value for V down in the bottom, okay, that we already converted to the cubic decimeters. So if I rewrite this, the n is 0.5 divided by 84, right? And I'm dividing by V, so I'm dividing by 0.250. Everybody okay with that?
Yeah.
Okay. So I'm going to scroll down so I have a little more room. All right. So here's where it gets a little tricky. This is where you got to remember like your like 4th, 5th, and 6th grade math concepts. Okay. Because what we're going to do here is I'm going to pretend, 0.25, I'm going to put it over 1 because it's like I'm dividing fractions, right? Because I have 0.50 divided by 84, but I'm dividing it by 0.250. So I'm going to put it over 1 because anytime I put something over 1, it's still itself, right? Because dividing by 1 doesn't change it. Now, what happens if I divide by a fraction? Who remembers what I do with this?
You switch it and then it changes to a multiplication.
When I switch it how?
Like the denominator and
Cross
the
butterfly or something like that.
Not cross multiplying, but I multiply by the reciprocal. So when she says switch, what she's talking about is this is going to flip and it's going to become the reciprocal. So if I rewrite it, it's now going to be 0.5 divided by 84 times, oh no. All right, hold on. Get us back together here. Okay, so it's now 0.5 divided by 84, and I'm multiplying, but I flip it. So now the 1's on top and the 0.250 is on the bottom. So anytime when you divide by a fraction, you multiply by the reciprocal, and the reciprocal means I'm flipping the numerator and the denominator. So I rewrite it. Now it looks like this. Okay, but now I can simplify it, right? Because I can get rid of the 1 because that doesn't do anything. So that means on top I have 0.5 times 1. So on the top I'm just going to have the 0.5. On the bottom I'm going to have 84 times the 0.250. Okay. So do any of our answer choices match this 0.5 divided by 84 times 0.250? Okay.
B.
Yes, B. Okay. If I come back up here and look, B matches what we just did. So not only did we have to kind of use our concentration equation to do this, but we had to kind of remember some of that math that, maybe we haven't used that in a while, with like fractions and reciprocals and all that kind of stuff. The one thing I do want to point out is that if you didn't do the reciprocal, you might have picked A. Okay. And also if you did not convert the volume, if you didn't convert this 250 to 0.25, you might have picked D. Because D looks exactly like B. It's just the volume did not get converted first. So, be careful of all those details when you're doing your practice questions and your work. All right, we're going to do one more. This one is similar to the last one in that they're not expecting us to actually solve, because if you look at the answer choices, they're all equation setups. Okay. This one is similar to some of the last ones that you guys had on your practice, where I'm actually going to use the concentration as a conversion factor in my calculation, my stoichiometry. Okay. And so this one this is kind of tricky because it's actually a limiting reactant problem. And I can tell it's a limiting reactant problem because it says, what is the maximum volume? And notice we're solving for cubic decimeters, but it's a gas, right? Okay, CO2 gas. And then if you notice down here, they give me the molar volume of gas, 22.7 cubic decimeters per mole. So because there's a gas, they're going to let me use that molar volume. So I'm going to have to use that in the equation since I'm solving for the volume of a gas. And then if I look at what I'm starting with, they gave me, it says it's produced when 1 gram of solid calcium carbonate, so that's one of my reactants, reacts with 20 cubic centimeters of this concentration of hydrochloric acid. So this is a limiting reactant because both what I highlighted in yellow and what I highlighted in orange, those are both reactants, because look right here, here's calcium carbonate and here's hydrochloric acid. So since they gave me amounts, they gave me values for both of them, I don't know which one is the one to use. So what we're going to do is we're going to set up both of them and we're going to see which one matches an answer choice. Okay. Now, what I would do to set this up, okay, start with the calcium carbonate one first. All right. So what I would do on that one is I have 1 gram. And I know that I would need to divide by the molar mass, and they gave me the molar mass of the calcium carbonate right here. Because again, they know you don't have a calculator, so they're not going to make you calculate the molar mass. So 100 would go down here. 1 mole on top. And then after that, I would need my mole ratio. Now on this one, this is all for CaCO3, right? So I need the moles of CaCO3 down here. And if I look, does it have a coefficient right up here? It does not. So that means it's 1 mole, right? Because if there's no coefficient, it's 1. And then if I look over here, the carbon dioxide, it's also 1. Okay, so I'm doing that molar ratio and I'm changing to the carbon dioxide because up here, that's what they told me that I wanted to solve for. Okay. And so then what I would do is the last step is, since they want the volume of that gas, that's where that molar volume come in. So 1 mole of CO2 is that 22.7 cubic decimeters. Okay. So if I simplify this and I get rid of all the ones, right? Because all the ones in the middle, none of these are going to change the answer, right? So if this is the correct one, then it would be 1 times 22.7 divided by 100. Okay. So if that's the correct answer, 1 divided by 100 times 22.7, which looks like answer choice C, right? It's written slightly differently. They have the 1 divided by 100 and then multiplied by the 22.7, but it's the same thing. So that's a possibility. But we also want to check the other reactant, the hydrochloric acid. So I'm going to erase this, okay? And if I now start again, I'm going to change colors. If I start with the hydrochloric acid, okay, because it's a solution, I always have to start with the volume, okay, but the volume is that 20 cubic centimeters. So I'm going to put in 20 cubic centimeters, and I know that we talked about the fact that anytime we have cubic centimeters, it's got to be changed to cubic decimeters, right? So I'm going to go ahead and divide by 1,000 because I know 1,000 cubic centimeters equals 1 cubic decimeter. Now that I have decimeters, now I can come up here, I can use this molar volume as a conversion factor. So this is the difference for solutions. For solutions, because they have concentrations, the concentration 2 moles per cubic decimeter. Okay, that's what it kind of reads if I rewrite it without that -3. I can use it as a conversion factor. I can say for every 1 cubic decimeter, there are 2 moles. Okay, that's what this means. That's what the concentration means. I'm allowed to do that because of the units that it has. So now that we have 2 moles, now I can do the molar ratio. So the molar ratio, HCl does have a 2 coefficient in front of it. So 2 moles would go down here. And then CO2 still doesn't have anything, so that's a 1 mole. And then I'm kind of out of room, so I'm going to have to continue down here because we do have that last step because they want us to solve for the volume of the gas, so 22.7 cubic decimeters. So the ending is still the same as my first calculation. So now if I simplify this, okay, I would have, let me scroll down a little bit. I would have, I have 20, and it's going to be divided by 1,000, right? Because that's the first thing here, 20 divided by 1,000. And then if you look here, look, I multiply by 2 and I divide by 2. Okay, we see how there's 2 moles on the top and then there's 2 moles on the bottom in the next box. So if you have the same number on the top and bottom, guess what? Just like the units cancel out, that number also cancels out. So I don't need to include those 2's in my equation because multiplying by 2 and dividing by 2, they're going to cancel each other out and it's not necessary to include them. So 20 divided by 1,000, all of the ones aren't changing anything. And then because we have a 2 on top and a 2 on bottom, we don't need to include them because they're going to cancel out. So the only other thing is then to multiply by the 22.7. So 20 divided by 1,000 times 22.7. Is there anything that matches that up here in our answer choices? Let me know if
It,
So is there anything that looks exactly like that?
no, not really.
Nope. So that means we just verified that we were correct and that C is the answer because it's going to be that first one we did. So, but if you look at the answer choices, like if you weren't paying attention and you didn't cancel out these twos, you might be tempted to pick B or A, okay? But C is the correct answer. Because if we checked both reactants and the only one that matches one of the answers is answer choice C, which was the first part that we did. All right, so I am going to switch us over to our notes now. So we're going to kind of briefly go over this from today. So this is what you guys have on Canvas. And it's sort of added on. So this is not in your notes that you already have, because really this has to do with sort of a lab technique and then how we use that lab technique with our concentration equation to do some calculations. So what you're going to see is a lot of times solutions, a lot of times are acids and bases, not all the time, but a lot of times we have acids and bases that are solutions that we use in reactions. And so what we're going to talk about is what is it called? What is that type of reaction called? Because you're going to see the term neutralization or neutralizing in a lot of questions. So I want to make sure that you guys kind of are aware of that. And then we're going to talk about this term titration. This is the lab technique that you use to gather data so that you can then do these calculations. And so in practice questions, you're going to be given the information, but in an actual lab setting, you could actually do the titration yourself and make the measurements and then use that data that you measured to then do the calculations. So kind of as I said, we're going to talk about what's a neutralization reaction because we need to be able to know that terminology if we see it in a question. Talk about sort of the formulas in neutralization reactions because they always follow a pattern and you need to be able to, you need to know how to write them. And then how do we actually do the calculation? And what's going to happen is we're going to have two solutions. One solution is going to be an acid. The other solution is going to be a base. And just like on that practice question with the antacid, I talked about that acids and bases neutralize each other. So when they react chemically, they kind of cancel each other out. Okay. And so what happens is you will be given, you know, a solution that maybe is an acid, and they'll tell you this is the concentration of it, and here's the volume that you used. Okay. And then they'll tell you how much volume of maybe the base you used, and you'll have to solve for the unknown concentration. And you can do that in a few steps using our concentration equations and using the mole ratio in your balanced equation for your reaction. So neutralization reaction, okay? Specifically, it's a type of double replacement reaction. Now, last year in first year chemistry, we learned about double replacement reactions. That was one of the types of reactions. There were other ones like synthesis and single replacement and combustion and decomposition. But double replacement has a few specific kind of subcategories, and one of them is neutralization. So the term neutralization is used to specifically refer to a double replacement reaction when you have an acid and a base as your reactants. And they always follow this pattern of producing water. So they're always going to produce H2O. And then they always produce a salt, which is an ionic compound. So when you have a neutralization reaction, if you remember that this is the pattern, they're really easy to write the equations for and predict the products. And if you missed something, this is on Canvas, so you can go back and fill it in if you haven't looked at it already. So I'm not going to pause long enough for y'all to write every single thing down because it is on Canvas. So on this one here, they've given us these two things. Now, here's how I know that this is neutralization, okay? First off, the second thing here, this is an acid. It has acid in the name, phosphoric acid, okay? Acids always start with hydrogen in their formula. So if I see the name phosphoric acid or if I see this formula that starts with a hydrogen, that's got to be an acid. I know that this is a base because all bases or most bases have hydroxide in their compound. So if something has hydroxide, that is a base. There are some bases that don't have hydroxide, but if it does have hydroxide, it's automatically a base. So calcium hydroxide, and then this is the chemical formula based on the charges. So if you if you don't remember from last year how to write your chemical names and formulas, you might want to, maybe go review your information from last year in chemistry, or look for something online to help you with that, because that is kind of a skill that you still need to have. But calcium hydroxide, because calcium has a +2 charge, that means we need 2 hydroxides to balance it out, because hydroxide is only -1. For the acid, hydrogen is always +1, so we need 3 of them, because this PO4, this is actually a phosphate ion, and so it's -3, and that's why there's a 3 here, because we need 3 hydrogens. Now, for acids, when you're trying to figure out what the products are going to be on these reactions, it helps people to think of the acid in terms of, like, how would I name it if it was an ionic compound? And so this is hydrogen, and then this ion is phosphate. So sometimes it helps us to think kind of in our head as this being hydrogen phosphate, because then that's going to help us write the names of the products and then their formulas as well. Because what's going to happen is this is going to follow a pattern. And in last year, we learned about, it's kind of like A, B plus CD. So calcium is A, hydroxide is B, hydrogen is C, and then the phosphate, the PO4, is D. And so they're going to rearrange and switch partners. So calcium, the A, it's always going to go with the D from over here, the phosphate. And then here, the one that's the letter C, which in this one is the hydrogen, it's going to switch places. It's going to pair up with the hydroxide. So this H plus the OH, that's what gives us the water, because the hydrogen from here always pairs up with the hydroxide from the base, and they make water. And then that leaves the other ions, the calcium here and the phosphate here, to make that ionic compound I mentioned. So that's what our 2 products are going to be, water and then calcium phosphate, because if you look at the names, that's what I would end up with. And so then if I write their formulas, hopefully we should know the formula for water. That's pretty easy. And then for calcium phosphate, because it's ionic, I do have to look at its charges. Okay, I mentioned earlier, calcium is +2. I know that because it's in group 2 on the periodic table. So again, if this is sounding like you're confused about charges, then you might want to go review sort of your charges on your periodic table and your charges for these ions like PO4, which is a polyatomic ion, because this is something that we learned last year in the advanced chemistry classes. So calcium is +2, phosphate on the list of polyatomic ions, it's -3. And so when I put them together, I need to have +6 and -6. That's the only thing I can get mathematically that will balance these. And so that means that I need to have 3 calciums, because that would 3 times this +2 would give me a +6. And I need 2 of these phosphates, because 2 times this negative charge would give me -6. And then the +6 and -6, that would balance out, which is what I want from an ionic compound. The other thing is, be careful, because I do need to have these parentheses around the PO4, because this 2 has to multiply to everything, the whole entire PO4 ion, not just the P or the O. So then I want to make sure I'm balancing it. Right now, it's easy sometimes to help when you're balancing to think of the water as the HOH, because when you're balancing it, it helps it to be easier, because I have calcium, I have hydroxide, I have hydrogen, and then I have this phosphate ion. So to make it easier to balance, sometimes it's just like we thought of this name up here being hydrogen phosphate instead of phosphoric acid. Sometimes it helps to think of water as HOH instead of H2O, just so we can visually see what's going on a little bit easier. So if I start off on the reactant side, these are my numbers. There's 1 calcium, because it doesn't have a subscript. There are 2 of the hydroxide. It's in parentheses, and there's a 2 outside, so it's multiplied by 2. There are 3 hydrogens, because there's a 3 subscript right behind it. And then there's only 1 phosphate, because this 4, that's part of the phosphate formula. So notice it's already in the parentheses. So there's only 1 of the PO4s. On the product side, if I compare, there are 3 calciums. It has a 3 subscript behind it. There's only 1 hydroxide, because remember when I rewrote this as HOH, there's only 1 OH here. There's only 1 hydrogen here. And then the phosphate, the PO4, there's 2 of them now, because look, it's in parentheses and there's a 2 behind it. So when I'm balancing, remember that my whole goal is to get these to all be equal. And so I'm going to have to multiply the calcium by something over here. So I'm going to have to multiply it by 3, because that will make that match. But that 3 also affects this hydroxide. So the 3 is also going to multiply by the 2 we already had for hydroxide. and it's going to change it to 6. So that means that I need to come over here and I need to put a 6 in front of here because I need that 6 to multiply by the hydroxide here to balance it. But that 6 also multiplies by the hydrogen. So both of them change. So now calcium and hydroxide are good, but the hydrogen and the phosphate are still not. But if I look on this side, I have 6 and 2. On this side, I have 3 and 1. So I need to double both of them on this side, on the reactant side. And since they're in the same formula, the hydrogen and phosphate, I can put a 2 in front of there, and it will double the hydrogen to 6, and it will double the phosphate to 2. And now everything is balanced. So my coefficients are 3, 2, 6, and then an imaginary 1. We just don't write it in. So how does this relate to solutions? Well, as I mentioned, we have a lab technique. It's called a titration. And a titration is where we take a solution of known concentration. It's called a standard solution. That's the term for it that you need to know. Standard solution means that it was precisely made in the lab using proper lab techniques. And so we know for sure what the concentration of it is. Okay. And we use that known solution to determine the concentration of the unknown solution. So what you do, okay, you measure out a known volume of the solution, okay, and then you put the other solution in what we call a burette. That's a piece of lab equipment, and you're going to see a picture of it on the next slide. And you add it drop by drop into the other solution that's in a flask until they've neutralized each other. Now, we call that the end point because that means we're done. That means the reaction's over and the acid and base neutralized each other, okay? So if you hear this term end point, they're talking about the fact that you've reached the end of the titration and the neutralization has occurred. How do we know that it's reached the end point? Well, we use a visual indicator, and we use so we can visually see. And so an indicator is typically something that is going to change color, so our eye can visually see that there is a change that has happened. And so the most common indicator for acid and base titrations is called phenolphthalein. It's this really long word. This is how it's spelled. But it's called phenolphthalein. And the reason it's really good to use is because when you put it in an acid, it's colorless. So it's clear. So it doesn't change the color of the solution. So typically you'll start off with your acid in your flask and you'll add a couple drops of phenolphthalein, and then as you add the base from your burette drop by drop, you'll see it'll start to turn pink. And what'll happen is you'll see it'll kind of swirl pink, but then if you swirl the flask, the pink disappears because it's not fully reacting. It's reacting, but then it's going away. And so what happens is you keep adding more and more drops of your base until that pink color does not fade, until it stays. And that's when you know you've reached the end point, because now that pink is not going away when you swirl the flask. So this is kind of visually what it looks like. So here's your flask, and here's where I have an acid of unknown concentration. And so the acid it's going to be colorless to start off with, but I'm going to put a couple drops of phenolphthalein in it and it still be colorless. But then as I add my base drop by drop from this burette, I'm going to see it start to turn pink, but it's going to disappear. And then as I add more and more, eventually it's going to reach that end point where it doesn't matter if I swirl the flask, it's going to stay this pink color. Okay. Now you got to be careful though, because you don't want to what we call overshoot the end point. If you overshoot the end point, that means that you've added too much of the base. So when this color change happened, you want it to be like a faint pink. If it's too bright or too dark of a pink, you've overshot the endpoint, and then your measurements are not going to be correct because you added too much volume here. But what happens is you know the volume of the acid down here in the flask, and you know the concentration, or I'm sorry, you don't know the concentration of it. But up here in the burette, you have your base, you know the concentration of it, and you don't know the volume at the beginning, but after you've added it and your color change happens, you use the burette. It has these markings on it. You measure the volume that you added into the flask. So you subtract, like where did I start versus where I end? And when you subtract, that tells you how much volume of the base you added. And so you know the volume and concentration of what's in the burette, and you know the volume of what you originally had in the flask. And so then you can solve for the concentration of that one. A lot of times this is milliliters, which is cubic centimeters. So we do always have to convert to those cubic decimeters like we've talked about in our practice problems. So the steps for doing this, Okay, the first step is you always have to have a balanced chemical equation because you have to have your molar ratio to use. Okay, what you do is you take the known concentration that you know, the concentration and the volume, and you use your concentration equation to convert it into moles. So I'm going to rearrange this equation to solve for moles, to solve for N. So I take the known concentration and I multiply it by the volume. That's going to give me the number of moles of my known solution. Then I use the molar ratio from the balanced equation to convert from moles of the known into moles of the unknown. Then I use the concentration equation again because now I know the number of moles of my unknown, and we know the volume because it's going to be either given in the problem, or if we're in a lab, it's going to be something that we measured. And so I can divide them to find the concentration of that unknown solution. So there are a couple examples. I'm going to try to get through them really quickly, but if you want to look at them again on your own later, you can. But here's kind of what a possible question would look like. And they're not always going to be the same because we're going to look at some more next time where it's slightly different. But here's kind of the basics. So here's the volume, 25 cubic centimeters of this concentration of this solution. Is this the acid or the base? This one that I'm circling. Can y'all see me circling it? I don't know if y'all can.
Yeah, we can see it. We can see it.
HF, is that an acid or a base?
A base?
Nope. Base is going to have OH. Acids always start with hydrogen.
Oh yeah.
So HF is acid. This is hydrofluoric acid. So they give us the known volume and the known concentration of that solution, and it's neutralized. So here's that word I need to know. That's just telling me that it's doing this type of specific chemical reaction. But it's neutralized by 47 cubic centimeters of an unknown magnesium hydroxide solution. So this is my base. So they want us to solve for the unknown concentration of the base. So we're going to follow our steps. So the first thing is to have a balanced equation. So I take these two. These are my reactants. Remember, one product is always going to be water. The other one is going to be the positive ion here with the negative ion here. So Mg and F. It has to be MgF2 because magnesium's charge is +2. Then I want to make sure I balance it. And then I can kind of fill in my information. So I know the volume and concentration for the acid. I know the volume of the base, but I don't know its concentration. That's what I'm solving for. Notice that I already converted the volumes to cubic decimeters. Okay, because again, I know that I'm going to have to do that before calculating. So again, that's kind of a good habit to get into. I just moved the decimal 3 places to the left. So step 1, I'm going to take the known information about this one. So I know the concentration and I know the volume. I'm going to plug them into that concentration equation, rearrange it to solve for moles. So I end up multiplying because if I bring the 0.025 to this side, it requires multiplication. So 0.28 times 0.025. That tells me I have 0.007 moles of the acid. Then I come up here and I use my mole ratio. Here's the acid, it's got a 2. The base, it does not have a number, so that's a 1. So step 2 is taking the moles of the known, which is the acid in this one, and I'm going to use that molar ratio, the 2 for the HF. The base didn't have anything, so it's a 1. So essentially I'm dividing by 2 here. So 0.007 divided by 2 is 0.0035 moles of the base. Then step 3 is then to take the moles we just calculated and divide them by the volume of the base that we measured originally, which is up here. We wrote it right underneath this formula. And I'm doing that, I'm dividing them because that's going to tell me the concentration. Because remember, my equation for concentration is moles divided by the volume. So when I divide those, I get 0.074, and then these are my molar concentration units, moles times dm to the -3, and it's the base, so I wrote the formula for that one. So that's essentially, like, that's the steps, okay? Now, could it be slightly different? Like maybe they don't ask you to solve for the concentration, maybe they ask you to solve for like the volume or the moles, yes. But the basic premise is the same. You're going to use the concentration equation in some way, and you're going to use the mole ratio from the acid, between the acid and base, to go between them, okay? There's another example on here. We're not going to have enough time to go through the whole thing because we only have about a minute or two before the bell, but the process is the same thing. So here's my acid and base, If I rearrange them, I'm going to get water, and then I'm going to get K and BR, and they're both +1, -1, so there's no subscripts needed here. It's already balanced. If I look at everything, everything's already balanced, so everything's a 1-to-1 ratio here. There's no coefficients. I fill in the information. So again, I converted this volume to cubic decimeters. Here's the concentration that I know. Both of those are for the acid, the HBr. For the other one, I know the volume. I just got to convert it to cubic decimeters. I don't know the concentration. So same exact process, okay? I'm going to solve for the moles of the known. So I'm going to have to multiply 0.195 times 0.037. I get this really small number. And now in this one, in step 2, really, like, you could skip this because we talked about in the equation, everything's a 1-to-1 ratio. So do I really need to show this? No, I could just say that the acid and base are a 1-to-1 ratio. And so that means that they are going to have the same number of moles. Okay, it's still going to be the same. And then I take the moles and I divide by the volume of that base. And that gives me my concentration of that one. Okay, so make sure on Canvas, your assignment, guys, is to make sure you have the notes and example filled in, and you're going to submit them just so that you can show me that you took the time and you did them. Okay, so you have that one, and then you also have your practice questions from the beginning of solutions from Tuesday. So make sure that you get both of those things submitted. I think the one is due tonight because I'm going to post the key for it on Saturday. And then this one from today, this is just kind of making sure you have these notes and examples filled in. And I think I made it due over the weekend, but you know, this is pretty short. You're just filling in the examples and stuff like that. All right, guys, so I'm gonna let y'all go because that was the bell that just rang. So I will see you guys. Oh, look, we had more people that joined. Hi, Mary. Hi, Christina. I didn't even see y'all came in the middle of things. All right, so you guys have a good rest of the day, and I guess have a good weekend because I won't see you tomorrow. I'll see you guys on Monday, okay?
Bye, Miss Thomas.